So we left off considering these three questions and how what we've done in 2 dimensions is going to apply to 3-dimensional vectors now. First thing we looked at is unit vectors in the same direction. So let's say I got this vector W here. If you want to draw a rough picture for it, so we're coming out +3 this way. Here's our x, here's our y, here's our z. So we'll come out +3, we'll scoot this guy over 5, we'll go down 1, so somewhere about in there. So we want a vector in that same direction, but that's only going to have a magnitude of 1. Okay? So we're going to use the same vector formula as before. You just take the vector on the top, you put it over the magnitude. So we need to find magnitude of W. And just apply it. So that unit vector is going to be now some of you guys have left them put together. I'd like you to at least split these apart. Rationalizing isn't a huge deal. You can or not. So it really depends how the book gives answers. But if you want to leave it like that, that's fine with me. Now just understand, if we squared each of these terms here, we would get a resulting thing of 1. So how do we do dot products? Well, when we did them in 2 dimensions, we took the A's multiplied by the A's, B's multiplied by the B's. Only adjustment we're going to have to make is account for the C. So I'm going to pause it here if you guys want to give it a shot, and I'll see you after the break. Remember, dot products tell us how 2 vectors interact with each other, and you get a number. Okay, it can be positive, it can be negative. Multiply the corresponding components, and that's what you should get. All right, we can now find the angle in between these 2 guys as well. So these guys are somewhere in space, and we want to find what kind of angle they make between each other. So we get a formula that says cosine of that angle is nothing more than the dot product on the top divided by both these guys' magnitudes. So we just need to do that exact same thing. So I'm going to dot them on the top. Okay, so let's take the -2 there. Now I need their magnitudes on the bottom. So I'll find magnitude of V. Square root of 14. Find magnitude of W. Square root of 6. And we'll get our calculator and see what angle that gives us. So we'll inverse cosine -2 divided by parentheses, square root of 14 times 6, 102 degrees. Okay, nothing we haven't done before, just one more component we have to account for in our calculations. Now, here's where it gets a little interesting. So we get these theorem direction angles. Okay, so we get some vector V. It's got I, J, and K components, so it has an A, B, and C with it. It's a non-zero vector somewhere in space. Okay, it has to have values or it won't be a vector at all. The direction angles alpha, beta, and lambda follow this. Okay, so we're looking for basically the angle that the vector makes with the I-axis, with the J-axis, and with the K-axis. So we're trying to find what the interaction between the vector and each axis. Here's kind of a picture, right? So a little bit crowded in here, but you can at least see your x-axis, your y-axis, your z. This is the guy right here that we threw some vector in, okay? And it makes some point P, and we can obviously put our box all the way around it. We're trying to find how this vector interacts with the x, interacts with the y, and interacts with the c, okay? These formulas will tell it for us. All you really have to do is take the a component, put it over the magnitude, okay? And that's going to equal cosine of alpha. So cosine beta is the b component over the magnitude. Okay? If you want to kind of follow the proof in the book here, it's kind of a neat little application with these. But these will be available to you guys. You just have to know what they're used for. So we're trying to find how the vector interacts or at what angle to each individual axis. So if I gave you this here, okay, vector v, negative 3i plus 2j minus k, first thing I'm going to need is the magnitude. Is square root of 14. Now, I know cosine of alpha is nothing more than my a component right here divided by my magnitude. I know cosine beta is nothing more than my b value over my magnitude. And lastly, I know cosine lambda is nothing more than my c value over the magnitude. I'm going to pause it here, throw these in the calculator real quick, and see if you guys agree with my angle. All right, so we punched it in our calculator. We found alpha 143, beta 57.7, and lambda 105. Now that doesn't tell us exactly where it is, just how it interacts with each axis. So to actually figure out where this guy is, we'd have to plot it and kind of get the, approximately what quadrant it's in, in 3 dimensions, obviously. But this at least tells us how it interacts with each axis. So if you go back to this picture here, you could now imagine those degrees in there. Okay, so somewhere in this 3-dimensional plane, you'll have a vector. How is each angle represented as to the x, y, and z axes? You saw I pasted this in here. We've done this part of that equation. Okay, if we want to represent that vector as far as its magnitude and its direction, we've used these when we've done airplane problems, force problems, all kinds of stuff. All we'd have to do is add in the little y thing here. All right. Think of any questions you guys have, and we'll start looking at this stuff in class.